Hey everyone, in this first video from section 5.4 we are going to talk a little bit more about the fundamental theorem. And so we're going to start out with this scenario. If we define y to be equal to the integral from a to x of f of t dt, we know from the fundamental theorem that that would be equal to the antiderivative of f evaluated at x minus the antiderivative of f evaluated at a. What I want to know, or what we want to find out more about, is what's y prime then? Well, y prime would be equal to the derivative of the antiderivative of f at x minus the antiderivative of f at a. And by properties of derivatives, we can split that into two separate derivatives, the derivative of the antiderivative of f at x minus the derivative of the antiderivative of f at a. Well, the derivative of the antiderivative of f at x is simply going to be f of x. The derivative of the antiderivative of f at a is going to be 0. Why is that? Because big F evaluated at a is going to be some constant that we don't know, but we know the derivative of a constant is 0. So that's equal to 0. Now, you might ask yourself, well, why is that important? Why do I care about that? And maybe I already knew that already from what we did in section 5.3 regarding the fundamental theorem. But I want to extend that a little bit, and I want to ask, what if y is equal to something like this, the integral from a to x cubed of f of t dt? Well, we know that that would be the antiderivative of f at x cubed minus the antiderivative of f at a. Well, if that's how we define y, what then is y prime? Well, y prime would be the derivative of f at x cubed minus the derivative, minus the derivative of f, big F at a. We already know that this will be 0, but what you may have forgotten is that the chain rule still applies. So the derivative of big F is going to be little f, evaluated at the inside, which is x cubed, times the derivative of the inside, which is 3x squared. So the chain rule there still applies. The derivative of the outside evaluated at the inside times the derivative of the inside. Well, what happens if we take that one step further and we say, what happens if we switch the limits of integration from a to x cubed to x cubed to a of f of t dt? We already know from properties of integration that this should be the opposite of what we just found. So let's see if that works. Well, that would be big F at a minus big F at x cubed, and therefore y prime would be the derivative of big F at a minus the derivative of big F at x cubed. And as you can see, that first derivative is going to be 0, and the second one is going to have a negative sign in front of it. So the opposite of little f at x cubed times 3x squared, which is consistent with our properties of integration that we learned earlier. So this is just an analytical approach to that. What I'd like to do next is I'd like to do a demonstration of this using Desmos. So here we go with our Desmos demonstration, and what you see is a graph of the sine function, and we are going to graph in line 6 the integral from a to a over 2, or sorry, x over 2, x divided by 2 And we're going to take a look at what the derivative of that looks like. So the derivative of that is what we're going to graph next. And you may be looking at that green function that just popped up there and saying to yourself, well, what does that show me? What is that the graph of? And let's think about that. If the red graph is the graph of the sine function, the green graph appears to be a graph of the sine function as well, except it has a period that is twice as long and an amplitude that is 1/2. So let's go back to OneNote and figure out what has happened there. So what we did is we took y is equal to integral from a to x over 2 of the sine of t dt. And we know that that would be the antiderivative of the sine function. So what function is the antiderivative of the sine function? That is the opposite of the cosine, evaluated at x over 2, minus the opposite of the cosine, evaluated at a. And then we found the derivative of that. So y prime is equal to d dx of the opposite of the cosine of x over 2. The two negatives make a positive, so plus the derivative of the cosine at some value of a. Well, the derivative of the opposite of the cosine is going to be the sine at x over 2 times the derivative of x over 2, which is 1/2. And the derivative of the cosine at a is simply going to be 0 because that's the derivative of a constant. And if we rearrange things a little bit, we have 1/2 sine of x over 2, which is a vertical shrink by a factor of 1/2 of the sine function and a horizontal stretch by a factor of 2. And if you go back to our Desmos demonstration, you will see that's what we have. I'm also going to demonstrate that rearranging the order of the limits of integration there. So I'm going to put the x over 2 as the lower limit of integration, and I'm going to put a as the upper limit of integration. What did that do? That simply flipped that original green graph over the x-axis, which is equivalent to changing its sign. And to make things even more clear, I'm going to switch the value of a up here just to show you that changing the value of a has no impact whatsoever. I'd like to do one more example, and in this example, I would like you to pause the video and think about what the final answer will be and how that will play out using Desmos. So our function is y is equal to the integral from a to 2x of the sine of t dt. So pause the video for a minute and think about what y prime is going to be and what it's going to look like when we graph it compared to the sine of t. So if you figured that out correctly, if y is defined as the integral from a to 2x of sine of t dt, then y prime, the derivative of y, should be equal to 2 sine of 2x. We're going to take just a moment here and put that into Desmos and verify that that's what we got. So our lower limit of integration is going to be a, and our upper limit of integration is going to be 2x. And if you look at the red function, it's the sine function, and the green function is 2 times the sine of 2x, which is a vertical stretch by a factor of 2 of the sine function, and it's a horizontal shrink by a factor of 1/2 of the sine function. So again, confirming what we figured out analytically. And that is it for the lesson for today.